Thanks so much for joining us for this NGSS ESS webinar. Today's webinar, Ocean Acidification, Bridging Earth Science and Chemistry. And this webinar is being presented by the NGSS ESS Working Group. Myself, Aida Awad, I'm past president of NAGT, and my colleagues Ed Robeck and Missy Holzer are also joining us, as well as Ashley Carlson, who's going to be working the dials behind the scenes here. Today, we have an amazing webinar presentation for you by Miasha and Jessica, who are from Arizona State University Center for Education Through Exploration. And we will have some time at the end for discussion and Q&A, although I know that they are going to engage us heavily throughout the course of the webinar. And then we'll have time for that post-webinar survey at the end. I would ask that during the course of the webinar, you consider that chat box to be kind of a classroom open discussion box. It's not just for questions, but it is for chatting. So any ideas, comments, thoughts that you have as they're sharing information, please pop those into the chat box. We will harvest questions from there, but we'll also like to keep track of all that conversation that's going on as you're hearing what they have to present for us. Little teaser here, look for an announcement coming out beginning of the year 2024, scary thing to say, that there will be a webinar in February, which we believe at this point is going to be entitled Geoscience Teaching and Learning in the Time of AI. So keep your eyes open for that one. We'll be bringing that to you. And as I said, please make sure that you're using that chat box to talk here with your colleagues as we go through this wonderful webinar. So Ocean Acidification, Bridging Earth Science and Chemistry. And I am going to stop sharing and turn things over to Jessica and Miasha. Go ahead and take it away, ladies. Thank you.
All right. Well, thank you so very much for the invitation and allowing us to take a little bit of your time today. And yes, we are here to talk a little bit about ocean acidification. Before we really get started and we dig into some introductions and tell you a little bit about us, we'd like to know a little bit about you. Maya, would you mind dropping the Padlet over into chat? So we have a quick Padlet to kind of find out where you all are from. So step one, you can either scan the QR code or you can click the link in the chat. Step two, in case you've never used a Padlet before, you're going to go ahead and click that little plus sign that's in the lower right-hand corner. Step three, up at the top here, you're going to see an option to be able to put in your location. City, state is fine. You don't have to get too specific. And then there is a step four. You can add additional stuff here. So some of the additional stuff, in this case, I dropped in the high school that I taught at when I was still in the classroom, and then also a little bit about what I taught. So give you just a moment to enter all of that information. I'm really excited to see where you all are from. Ooh, can you guys see my screen? Can you see the map? Or is it still the presentation?
We see the map.
Oh, that's amazing.
Yeah.
Very helpful. Oh, look at us all over the country. I like how the little pins populate. A little bouncing action. This is great. And see, we can hover over. This is great. The good life. I love it. These are great. All right. Well, thank you so much for playing along and giving us kind of a sense of where you all are from. Let me slideshow again. Let me verify you can in fact see the slideshow.
We can.
Great. All righty. So let's introduce ourselves real quick. So we are the Infiniscope project. We are based out of Arizona State University in the Center for Education Through Exploration. This is one of many projects that are hosted by the ETX Center. I myself am Jessica Swann. I am a former classroom teacher. I was actually in the classroom for 9 years, taught earth science, I taught biology, I taught integrated science, I taught physical science, pretty much just didn't teach physics and didn't get too deep into chemistry. Currently, my role in the ETX Center is I'm what's considered a program architect, so I specialize in communities of practice. And for Infiniscope, I am the Infiniscope community manager. And with me today is Maya. Maya, introduce yourself.
I'm Maya. I'm a learning designer with the ETX Center. I also have teaching experience, only 2 years though, but I taught math and computer science, and then I've got a background in physics and astronomy. I'm one of the learning designers for ETX as a whole and also for Infiniscope, and I actually made the ocean acidification lesson we're going to talk about.
Yeah, Maya is actually the real star of the show, so I'm just going to tee things up and then she's really going to take over and do some amazing things. So your first question might be, if you've never heard of us, never met us before, well, what is Infiniscope? So Infiniscope is a digital teaching network. And what we do is, you'll see down here at the bottom of our pyramid, the very first thing that we do is we create NGSS designed and aligned, adaptive and interactive digital learning experiences. The real key word that I want to hone in on there is the adaptive piece. As we go through, as Maya is really sharing with you about the way that this ocean acidification lesson is laid out, you'll get a much better sense of what we mean by adaptive. But in this case, what I want you to take away from that is it's a level up from interactive. So we're able to do some very sophisticated things with the technology that we use, the backend that we use, to really motivate your students and push them through these digital learning experiences. We focus our content on the Earth and space sciences. The reason we do that is because we are a NASA-funded project, and our content primarily focuses on middle school and high school. The second thing that we do is we ultimately want to be able to catalyze creators. So it's not just about the stuff that we make, but it's also about the stuff that you can make and things that you can share. So we provide our technology platform to all educators that are members of our network so that they too can create their own immersive NGSS designed and aligned, adaptive and interactive digital learning experiences. On top of that, at the very top of the cake, you'll see that we also provide training. So we don't just send you out into the ether and we're like, hey, we have these amazing things that you can use. Go build your own thing. We actually provide you guidance. We provide scaffolding. We do some really deep summer training. So if you're really interested in digging in and learning more about how to create something that's really high caliber, we can do that with you over the summer. And then throughout the school year, usually during the fall, we do more smaller trainings, like 30 minute sort of interactives. Right now, we're finishing up our Tinker Time series. That's just little 30-minute segments on how to get into this new authoring tool. So our overall goal in the ETX Center is to transform learning so that we can embrace exploration of the unknown and at scale. The key word there is at scale. Many times I'm asked, why do we do digital? The reason we do digital is because it allows us to be able to create these really high caliber lessons and be able to distribute them nationwide. And our philosophy is to leverage curiosity of our students to drive them to do some exploration and ultimately lead to discovery, which, as you all know, discovery typically leads to additional curiosity. So this is what we talk about in the ETX Center, but you as educators know this is something else. Anyone want to drop in chat what you would call this instead? Any ideas out there? Anyone? Ooh, learning cycle? Yep, the 5E inquiry model. So, you know, we are over here just reinventing the 5E inquiry model. We just made it 3 things, a C, an E, and a D. Anyway, so what I want you to know is that because we do design everything with this learning cycle, you can rest assured that the inquiry model is built into all of the lessons that we create. So now that you have an understanding of who we are and a little bit about what we do, let's talk more about why ocean acidification. Why are we doing this lesson that kind of bridges this gap between chemistry and earth science? And really the story all kind of begins in a little bit of history. So way back in the day, we had No Child Left Behind. And I got caught up in the No Child Left Behind era because I was one of 3 teachers in the entire state of Arizona that was credentialed as an earth science teacher. So No Child Left Behind comes on board, And as one of 3 credentialed earth science teachers, my earth science class, gone. Just completely removed from the curriculum. We rewrote the entire curriculum. The expectation was all standards for all students. The same is true today. So even under NGSS, even under Every Student Succeeds, the plan is, or the idea is, that all students will be exposed to all standards. But if you don't have credentialed earth science teachers, there comes the problem. We'll talk a little bit more about that as we go through. But most courses, most high schools, as you know, typically use this 4-course model. So you have 4 science classes that are offered. Your kids are either required to take 2 or 3 credits in order to graduate. So there comes this question of, how do we get students exposed to all standards when they're only really required to take 2 or 3 science courses? Well, this causes problems such as, like I said, you only have 2 or 3 science courses. We have the lack of our earth science credentialed teachers. And ultimately, you need to reshuffle the workforce in order to make this happen. And massive teacher shortages won't allow us to reshuffle that workforce. So enter what's called the 3-course model. So the 3-course model really folds earth and space science into all of the other content areas. So it draws earth science into physics, draws it into chemistry, draws it into biology. And the courses here are called things like, and this is very explicitly coming mostly from the state of California, but it really applies across the nation as you are integrating the 3-course model. But these courses are things like physics of the universe, it's chemistry in the Earth system, and it's the living Earth. So the big thing here is it's an integration model. Now, if you know anything about NGSS, you know NGSS is all about integration. Our old model is all about silos. So back here in the 4-course model, we're siloing our science. 3-course model actually forces us to do some more integration. Now, I'm so glad I really did that nicely. It appears I forgot my animations on this screen, so bear with me as I walk you through this. So as we look across the states, so we did an analysis back in 2020. And in that analysis, we looked to see which states were using this 3-course model, which states were using 4-course model, and which are doing an ultimate blend. So ultimately, what we found is that 17 of these states are pure 3-course model, 5 use the 3-course model in kind of a non-traditional method. And then there are 12 states where there's a blend between the 3-course and this 4-course model. Ultimately, what that meant was when we tallied everything up, just in the top 2 rows, not even including the states that are doing both 3 and 4-course model, what this meant was on the order of almost 7 million students, high school students across the US are in this 3-course model. So as teachers in this space, something that we know, well, physics teachers are going to be able to pick up the earth science content pretty easily. Many times they're already teaching some of that earth science content in their courses. So you're going to see it in things like Kepler's laws. You're going to see it in things like HR diagram, which is not really, NGSS, but stellar life cycle is NGSS. Things like the fingerprints of life. All of these things fold into physics very nicely. Where in biology, the things that a biology teacher would typically teach are things like fossils and rock layers and relative age dating. They're going to talk about ecosystems. They're going to talk about climate change and its effect on these ecosystems. So that falls in really nicely. But now we have 2 other content areas, our traditional silos, that there are a couple of issues. Number one, our earth science teachers, well, they're just kind of non-existent, so there's not much to say there. But then when we look at our chemistry teachers tend to be a bit more confused. How am I going to integrate all of this earth science into my classes? If you're not already teaching an environmental chemistry course, this is not a natural connection for you. So As educators that work within this Infiniscope project, we see this, we saw this as the rub, we saw this as the potential issue, and that this is something that we felt we were capable and equipped to try to tackle. So in comes our concept, what it is that we're trying to accomplish. So what we're trying to do is fold in some of this core chemistry content with some earth science and sustainability core content and mesh them together with these things we call these flagships. So a flagship is a really large lesson like what you're going to see today that Maya is going to talk about, this ocean acidification lesson. And we're going to bring the nature of matter is going to be part of our home planet. Interactions of matter is about our changing planet. Matter and energy talks about how we can have a sustainable future planet. In addition, our educators that are in our network can be part of this evolution and build something that are called discovery lessons. These are smaller lessons that help to build content around the flagship, help to fill in some of the gaps along the way, maybe some of the more pure chemistry content, or maybe it's pure earth science content. Ultimately, at the conclusion of this, we want to be able to create these lab suites with our lessons that are at the core of that lab suite, and that you as educators can take that lab suite and you can, I don't want this, I don't want that, but I do want these pieces. And you can remix that so that it fits best for your classroom. Now, before I hand off to Maya, and I think this is my last slide, just to kind of tee her up a little bit. As we're talking about the lesson, or two lessons actually, it is now titled Our Changing Oceans. So these are our objectives that we have written for our formative objectives for the lesson. And then these are the standards that we're aligning to. What I've done here is I've created these little logos for you so you can see where we're pulling in the chemistry, and you can see where we're pulling in the earth science content, just to kind of help you track and kind of keep score along the way. All right, and with that, now that I've teed it up, Maya, you're on.
All right. So as just mentioned, our lessons, it was one long lesson titled Ocean Acidification, but we decided to break it into two different pieces. These smaller chunks can be done in a traditional 45 to 60 minute class period, so you can do them with your students. So we've named it Our Changing Oceans. Part 1 is Shell Shocked, and this goes into how oysters in the ocean are struggling to survive. And then part 2 is Our Changing Oceans Out of Balance, which dives deeper into the changing ocean chemistry. So at ETX, we normally start planning our experiences around phenomena, in this case, ocean acidification. From there, we start to think about what a simulation might look like that can help address the phenomena or any misconceptions associated with it. Seeing as how Infiniscope is NASA funded, we try to incorporate as much NASA data as possible. So the simulation you're about to see integrates data from both NASA and from NOAA, and it graphically presents how various environmental factors have changed. NASA's contribution comes from a couple different satellites, and NOAA's comes from a climate model. These are the satellites, Terra, Aqua, and Aura. So we're going to let you play with this sim. If you go to this URL, which we can post in the chat, awesome, Jess is on top of it. So you go to this URL and you'll be able to access the visualization lesson, which lets you interact with the simulation. There's no need to get an account at this point. Just confirm you're not a robot, enroll as a guest, click the button to go to course, and then open the visualization. You might also have to prove you're not a robot. So I'll give everybody a couple minutes to get in there before I continue on. All right, so I'm gonna assume that we're making our way into this visualization, and I'll start to talk about it while you might still be getting in there. So there are two modes to this sim, the graph mode and the map mode. Here we're looking at the map mode first. In this, students are able to select the variable they want to investigate from the dropdown and see how that variable has changed over time. Each variable has a slightly different range of dates. You'll notice that some go from 1800 all the way to 2020, others from 1980 to 2020. Some don't actually change at all. There are a couple other controls on the map view that let you hover over different locations to get the readout of the data, so you're not just going solely on color. You can click a button to allow the map to go full screen, and there's a little Earth globe button that lets you see the map on a globe rather than just two-dimensional. There's also a graph tab you can click on. The graph is a little bit more complex than the map. There's an x-axis, which defaults to time, and two y-axes, so variables can be compared. So when time is selected on the x-axis, you can see how different variables have changed over time, such as atmospheric carbon dioxide and pH, for example. You're also able to select a different variable for the x-axis, like hydrogen ion concentration, and then you're able to see the relationship between that hydrogen ion concentration and other variables like atmospheric CO2 or pH. But so far, what you see on screen, all of this probably only shows past and present conditions. With the NOAA model in there, we've also got future predictions up through the year 2100. So there's a button on screen that says future predictions. And if you click that, it unlocks the climate model part of the simulation. For some variables, you can see and select the emission scenario you want to use. The emission scenario basically tells us how much CO2 emissions are we humans putting out, and it goes from low to high. And you can see how the variables, for example, heat content, change up through the year 2100. Some variables default to the high emission scenario, and others are not included in the climate model at all. Then there's the similar functionality for the graph, where you can choose the emission scenario and view the trends and relationships up through the year 2100. So I'll let you guys take a couple minutes to explore the sim, play with the different controls, and then we'll keep going. I also want to make sure that everyone's able to access the sim. So if you haven't been able to, maybe post something in chat. So I noticed a question in here on what observations do we think our students would be making as they explore for the first time? And I'll go over this a little bit more, but we don't actually give the simulation right off the bat and say, go wild. We introduce it to them in a scaffolded sort of way. That way they start with, actually they'll start with just the map of aragonite saturation currently, not even over time, and they'll make observations. Then we'll slowly unlock new features, letting them see how it's changed over time, letting them pick different variables, eventually opening up the graph section so they can graphically see how different things change. So we don't want to overwhelm them by giving them everything at once, although there are times in other simulations and other lessons that we do that. But in this particular one, we scaffold what's available to them. And as they go throughout the lesson, they're essentially unlocking additional pieces. So I'm gonna continue on, and feel free to keep playing now or later. It's yours to play with. Yeah, let's go to the next slide if we can. So we're going to talk about the narrative for this lesson. Now, like most of our experiences, our Changing Oceans has a central narrative. We do this for a couple of reasons. We found that using a narrative where students assist characters in solving a problem employs some pedagogical strategies that encourage engagement through empathy and purpose, make the learning journey less about immediate mastery and more about this collaborative discovery. And doing this takes the emphasis off of and takes the pressure off of individual performance and getting the question right the first time, and really allows students to learn and engage and realize that it's okay to make mistakes. Now, I've also done some surveys with students from different grade levels and classes, and we found that it's like having a buddy. They like having something there with them for their learning journey. And these buddies are influenced by factors like how cute it is, what the personality is, does the personality resonate with them, and just personal preferences. We found that overall students generally have a positive feeling about their buddies. Many find them helpful in providing hints and support for their learning, and they express a desire to have a buddy in all these lessons. So all of this factors into the decision for our narrative, which is centered around Olympia, as you see on screen. So in our Changing Oceans, students meet Olympia, an oyster that lives off the coast of California in the San Francisco Bay. If you know anything about oysters in the San Francisco Bay, then the name Olympia might make sense because they are Olympia oysters. So Olympia is tasked with overseeing the well-being and development of young oysters. And she's noticed a distressing trend that many of the oyster larvae don't reach maturity and their shells are smaller and more fragile than they used to be. And Olympia is well-versed in the oyster life cycle, but she lacks the knowledge in chemistry. So she needs the help of the student to understand why the oyster larvae population is decreasing, why the shells are weakened, and needs the student's chemistry expertise to piece together the puzzle. So before we go on to the flow of the lesson, I'm going to talk about some key design principles that we have here at ETX that we use while designing our experiences. So the first one is pathways. Jess, if you can click to the next slide, please. Thank you. So one of the key principles we do is pathways. Pathways ties into student agency. We want students to make decisions and take charge of their learning journey. Pathways is just one way we do that. So using a hub and spoke approach, we present students with an opportunity to dive into the study of aragonite and oysters, and they have the choice of which one they want to do first. They can begin by understanding the chemistry of oysters or observing oyster larvae. But either way, every student explores both topics. But by letting them choose the order, we give them a sense of agency and that feeling like they're driving their learning and they're being able to explore in the way that they want to. The next thing, the next key aspect, key design principle we use at ETX is feedback. If we can go to the next, thank you. So we designed feedback to be adaptive. Our learning experiences are engineered to mirror the guidance of educators. We provide students with immediate feedback, constructive feedback that's tailored to their individual interactions with the platform, whether that's a specific response, the duration they've spent on a question, the number of attempts they've made, or even if they just click the next button without following directions and interacting with the simulation. We're able to track all that and provide feedback. And this feedback might manifest as hints, explanations, images, supplementary materials. We can bring them back to a section of the lesson that they've already done to show them, wait, you already learned about this, let's go visit it. We can bring them down alternate learning loops where they can get some remediation and some scaffolding to be able to come back and answer a question. There are all kinds of things that we're able to do with our feedback to scaffold and enrich understanding and support deeper, more nuanced learning. So I think I have a couple examples here of different feedback that a student might get if they interact with this screen. Each time the student answers a question a little bit differently, they get feedback specific to what they're doing. And in this case, students are dragging ions into this drag and drop image to understand what happens when carbonic acid dissociates. All right, so now we can get into the flow of the lesson. So I lied. Now we're going to get into misconceptions. So there are several misconceptions about ocean acidification that students, and let's be real, most adults have. One of these is that ocean acidification isn't a big deal because the changes we're seeing aren't significant. So to tackle this misconception, we use a simulation and students dive into the study of pH, and they examine the fluctuating concentration of hydrogen ions in the ocean, and they calculate the change in pH from 1980 to 2020. And they recognize that while these fluctuations might appear minor, it's only it's less than a 0.1 decrease in pH. So that does not seem like a big deal. So it appears minor, but really it operates on a logarithmic scale. So even though these slight variations in pH, they indicate significant shifts in hydrogen ion concentrations, which comes out to about a 20% increase in acidity. All right, if we click next, I think, yeah, so this is that 20% increase in acidity. And then we've got one more misconception that students will cover. So students take their observations one step further and address another misconception that ocean acidification means that the ocean is actually becoming an acid. So students conclude that although the ocean's pH remains basic, it's decreasing and it's shifting towards acidity, which is leading to the phenomenon known as ocean acidification. Now we'll get into the lesson flow. So I'm gonna show these as one big lesson, but I'll mark where we break, where the natural break is. So this first part is our changing oceans shell shocked. So students start out by meeting Olympia and understanding the core problem, that oyster larvae are struggling to survive and that the shells of these oysters are smaller and weaker than they used to be. In order to understand why these oysters are struggling, Olympia suggests that the student should do some research and see if this is a localized problem or if it's happening everywhere. Another thing we have, Olympia has a lot of faces. She's got a pretty strong personality. And so depending on what the student does, if they answer a question wrong, answer it right, her expressions are going to change. If she's talking about something sad, she's got a sad face. If she's confused by something, she's got a thinking face. We found that students really enjoy just these minor changes in the personality. So to understand if this is a localized problem or not, students observe the aragonite saturation state. So this is the first time they see the simulation. And as you can see, there aren't a lot of controls on it. We've just got this map of aragonite. And we learned that these maps are important because oyster shells are made of aragonite, which is a mineral made of calcium carbonate, and that oysters build these shells from the calcium and carbonate ions found in the ocean water. So this aragonite saturation state provides crucial insight into the health of oysters. Students use this simulation and they observe global aragonite saturation states. And they identify that in some areas, the saturation state is low, in some it's high. And it tends to be all over. There's no one place where everything's low or everything's high. So then students track aragonite saturation states over time, and they notice a general decrease. So we've got a video that kind of shows what the student is seeing, and they're able to do that. Oh yeah. And it might be hard to see just from here that it is decreasing. So we've also got instructions to help students hold their cursor over any place on the map and compare the values, because we found that no matter where you are, the saturation state has decreased. So once we make those initial observations and analyze this data, we go on a little bit further and we take a look at some images of oyster larvae shells and make observations, noting that the shells are thicker and smaller than they were before. Following this, students start to learn about oyster chemistry, how oysters used both calcium and carbonate ions to form their shells, and the role of hydrogen ions, how hydrogen ions have a tendency to bond with these carbonate ions. And when this happens, it's harder for oysters to form their shells because there's less carbonate available for them to make their shells. After going down these pathways and learning about this material, students put it all together. So they complete this oyster investigation and realize that as hydrogen ion concentration rises, the carbonate ion concentration decreases, and this affects shell size. Shell size makes it harder for oysters to make their shells. And so this wraps up part one of the experience, shell shocked. Part two goes more into the chemistry, out of balance. So after being re-antiquated with Olympia, students dive right back into the content, and they unlock another piece of the data viewer, the graph. And students are able to look at the connection between hydrogen ions and pH and track pH changes over time, understanding the implications of even small changes. This is also where students recognize a nuance. Even if the ocean remains basic, the decline in pH is indicative of ocean acidification. So then we start to dive a little bit deeper. And at this point, we've determined that oysters are struggling because of an increase in hydrogen ions and a decrease in carbonate, but we don't know why. What's caused this increase? So we use the graph, a simulation, to investigate the link between increased hydrogen ions and other variables. And ultimately, we note a very similar trend between hydrogen ion concentration and atmospheric CO2. So the students here, they click through a different, they're actually using the right y-axis, and they look at different variables, or the left one, and they compare these variables and see the one that matches is atmospheric CO2. And from here, students explore various forms of carbon in the ocean, and they're able to make a hypothesis about their impacts. Yeah. So here we see the relationship between CO2 and hydrogen ion concentration, and it's almost spot on. And here they're introduced to the different forms of carbon, and they're able to make predictions about what they think is going to happen based on what chemistry knowledge they already have. So now we really get into the meat of what's going on. Students dive into the chemistry and figure out what happens when carbon dioxide interacts with the ocean. They start exploring concepts like dissociation and the relationship between acids and hydrogen ion concentration. We're able to compare each student's predictions to actual data and discover gaps in understanding. And when students do have these gaps, we introduce concepts like Le Chatelier's principle, buffers, and chemical equilibrium. And these key pieces all together enable the students to complete the puzzle and realize that the increased atmospheric CO2 leads to higher ocean acidity and reduced carbonate ion concentration. And once students are able to put this all together, they're now equipped with the knowledge to explain this to Olympia, explain the challenges faced by oyster larvae and the deformities in their shells, and why this is all due to changing oyster chemistry, changing ocean chemistry. And that wraps up the experience. The students explain to Olympia what's going on, how this increase in CO2 is the ultimate cause for the oyster larvae struggling. And Olympia is able to take this information once she understands it and bring it back to the Oyster Council so that they can know what's going on. And that's the Our Changing Oceans, part 1 and part 2 in a nutshell.
All right. Thank you for that, Maya. And so with all of the learning experiences that we do, we actually do some significant classroom testing. So this particular lesson, we've done not significant, we've done a couple of classroom tests with it. So we like to go out, we do it, we test locally, because we want to actually observe students playing through these experiences. That tells us a lot about whether or not we've hit the mark and what kind of modifications that we need to make. So actually, when Maya's talking about the fact that we've split this lesson into 2 separate lessons, that was a direct result of the fact that when we were doing our classroom testing, the lesson length was way too long. And we kind of figured that that was the case, but we were like, you know what, let's test it. Let's see what they can do. Let's see how far they can get. And then we'll make some adjustments from there. So the one thing I do want to note is that because we have only been able to test it in 2 different local high schools, we do distributed testing where we get a lot more impact data and have a better understanding about how students are interacting and what they're learning. But based on the 2 small tests that we've done, when the students were asked why there was a relationship between ocean pH and oyster larval shell health, both of these classes tested with some statistically significant gain. So we're hoping that when we go to do this as distributed testing, and we'll see that that holds true. A difference between the 2 classes is that class 1 showed significant gains when it came down to drawing a correct inference from a table of the data that represents the oyster health and the ocean pH, where the other class did a much better job with understanding that the misconception of ocean pH is neutral or even acidic rather than slightly basic. So that's, like I said, that's some early data. And what's coming next? So what's next for us? So you'll see here, we haven't released this officially on our website. We're this close. I want to say within the next week, it's going to go up. But then the next thing, our cute little turtle, we've got some nitrogen cycle lessons that are also 2 lessons that will be coming out. Same philosophy. It's a combination of earth science and chemistry. But then also, as a little teaser for you, in the future, coming soon, right now we already have a way to kind of put these lessons or package them into something that we call a collection. In the future, you're going to be able to open up those collections. You're going to be able to customize the curriculum within the collection. So we may package it one way, and you say, yeah, but I want to add this other lesson or these other 2 lessons into my section, and you can add those. And you can also go and say, but I don't want this actual piece. And the reason that's going to be really powerful is with the way the lesson suites are packaged, you've got that flagship that I told you about previously, but also that we've got these discovery lessons that our teachers in our network are creating. So you've got some prerequisite content that can be built in, some prior knowledge builders. You've got some elaborates that you can kind of bolt in to the lesson. And sometimes those things resonate or they don't resonate. You need to cover it. You don't need to cover it. I've already covered it. Oh, this is great. I get a win. So we've got this remix option available to you coming down track. So those are things to look forward to. And then finally, just a last bit of one little beat here. As I said previously, when I introduced myself, is my job to cultivate these communities of practice. So if you're not familiar with what communities of practice are, there are 3 prongs to a community of practice: the domain, the community, and the practice. And we invite you to become members of this community and create your own learning experiences. I'll drop the join link over here in chat in case you've missed it.
Wonderful. Thank you so much, ladies. That was a wonderful presentation. We've got a couple of questions that have popped up here in various places. One of them is kind of a 2-part question. Are there suggestions for integrating the lessons into a particular unit of study in a chemistry course or an earth science course? How do you really identify, where it fits perfectly into that kind of curriculum?
Oh, that's actually that's a great question.
Yeah.
So I mean, I think it kind of depends on which silo you're technically teaching in. So if you're teaching in a chemistry course, we could find something like this may benefit something earlier in the year. So when we're talking, when you're talking about ionic versus covalent bonds, when you're talking about balancing chemical equations, those sort of things, it might fit better in the earlier parts. But if you're really teaching something that's more of a pure earth science, or maybe it's even a biology course, ocean acidification typically is taught towards the end of the year. One of the reasons we have small data is that when we deliver the product, most of our teachers were done teaching ocean acidification. So we've got to wait for it to come back around.
Yeah.
I don't know if that answers the question.
Well, I think it gets at the point. And then there's kind of another associated question about thinking about different levels. We talk about differentiation, and this seems that, you're making this connection between the student and Olympia, and maybe a small group of students at Olympia. Are there any ways to level this up or down to differentiate that content?
Oh, that's an excellent
Some
question.
of it's a little beyond that, the boundaries for grades 6 through 8. We recognize that. Some, how do you deal with that?
Yeah. So I have a good news, bad news sort of situation. So the good news is technically everything that we create, once you're a member of our network, you get access to it. So you can kind of tear things apart under the hood if you're interested in doing something like that. So you can go in and say, you know what, the language in this is just too high. Like the content's right, but the language use is just way too high. I want to bring that down a notch. You can go in and make those sort of modifications. The bad news is that for the larger things that we build, we do use what's called our advanced adaptive tools. So you do need to have a little coding experience to make that happen. But we can teach you how to do some of those things so that you can dig in and learn how to kind of modify the language. Other than that, you can also do things like just break it into smaller chunks. If you just want a little piece of it and say, you know what, I want just this piece. I'm going to delete all this other stuff. You can do that also. Again, we would recommend letting us connect with you just to make sure that when you do break that apart, that you don't break something that was critical, because you are talking a tech platform and things are connected. So we want to make sure that you're not delivering a broken product.
Yeah, and then Jessica, is there kind of a backside of this for teachers to work on that might, be a teacher dashboard or some rubrics, or where they're activating prior knowledge, those kinds of things?
So we do produce, let me see if I have that one available. I might actually have it up on my desktop here somewhere. So we do create lesson documents for everything that we create. Not there. If you can bear with me for just a moment. I'm pretty confident I have it up on my desktop. She says.
And I'm guessing, I'm just thinking back to your introductory comments while you're searching there for that, about the summertime workshops for teachers that really dive into this. And I'm guessing that a lot of those kinds of ways that you're going to prepare yourself for this blended learning, this adaptive learning platform. The backside for teachers are probably going to be present in those workshops over the summer as well.
Yeah, so we really spend a lot of time digging into, we do some of the pedagogical principles on how to create something that is highly interactive and adaptive. If you want to use something like right off of the shelf, all of our lessons have these the newest lessons have lesson documents like these that are attached. They give you some of the general information, you know, like prior skills before they come in, they need to have these skills, and during the lesson, they'll build these particular skills. We talk a little bit about what pieces of the entire collection can be found. So what prior content is developed around it and where it fits in the 5A inquiry model. We're designing our own pre-tests and post-tests, so you'll have those things available to you, so you'll know how your students grow before they've done the lesson versus after they've done the lesson. And these are things that I said we can remix, that you'll be able to pull out the pieces you don't want and keep things. It's all fully integratable into Canvas, into Blackboard. We're this close with Schoology if you're working on Schoology. I mean, you can technically use it in Google, but it's not a learning management system.
And then there was one last really quick question before we wrap things up. We've got some other things to tell you about, so please don't go away. But the last quick question here was, so the whole thing with the oysters and the lesson, it's all in Infiniscope.
It is.
Yes,
it will be. It's this close to publishing, so you got to keep checking back. It's not live yet. Technically, you got a sneak peek.
Yay. Awesome. I'm going to take us through a quick wrap up here. So if Ashley, I wonder if you could grab that link for the post-webinar survey maybe and drop that in the chat box. If you do need a certificate of webinar participation, the only way you can get that is through completing that post-webinar survey, but please do complete it either way. We really love to have your comments following up on the webinars. It's very helpful for us in planning future webinars. And also, please check out the NAGT website under resources under K-12 teachers. There is a listing there, which is currently being refreshed for opportunities for PD for 2024. So if you're looking for those opportunities as a teacher to participate in, or if you're as an organization wanting to list those with us, please make sure that you check that out. Links are available there on that page. So NAGT website, resources, and K-12. Also like to invite you on behalf of NAGT to check out our other webinars. We have a full webinar series as well as many member benefits of NAGT. And then Nesta, I know Missy is on the call, but she's not able to grab a mic right now. So I would like to tell you that Nesta is an organization that is also a sponsor of this webinar series. They are the K-12 Earth and Space Science educators and those who are interested in K-12 Earth and Space Science. Nesta members enjoy a monthly e-newsletter with timely announcements, a quarterly peer-reviewed journal, that's the Earth Scientist, and networking via social media and outreach events. And you're invited to join the Nesta community, which is a community of teachers by teachers. And pass this on to Ed. Do you have a mic open, Mike? There, Ed?
I do. Thank you very much,
great.
Aida.
Yeah.
And thanks to our presenters. Thanks to everybody for being here. And I'll just say very quickly that the American Geosciences Institute provides a range of resources for you as earth science teachers. And so please visit our website there and poke around. One of the things I'll definitely mention is that we facilitate Earth Science Week, which is the second full week of October each year. But we don't want it to be just that week. We want Earth Science to be recognized and celebrated and taught all year long. So please look for the resources that we have available, and looking forward to any contacts that you might want to have with us. Thank you all for being here.
All right. Appreciate everybody's time this afternoon. I hope you enjoyed the Infiniscope information. Please check that out on behalf of Missy and Ed and Ashley working things in the background there at CERC. Thanks very much. Have a great afternoon, everybody.
Thank you.